Hello, my name is Tom, and it'll be my pleasure to talk to you throughout a series of 6 programs concerning a relatively new MIG welding process. For the course of these programs, I'm going to make the assumption that you're familiar with and know how to weld using the MIG process. Oh, it's been around a while, but some recent developments in power source technology have made the process more versatile and therefore more popular. This series of programs will be in 2 parts. This is program 1. It's called, What is Pulsed MIG Welding? We'll start to answer that question in a moment. Program 2 is Pulsed MIG Process Variables. Program 3 will deal with equipment setup and weld preparation. And during program 4, we'll demonstrate some tips and techniques you can use to take advantage of the Pulsed MIG process. Keep in mind that these programs are to add to your knowledge of the process. You already know how to MIG weld, right? The second part of the series will consist of 2 programs. These 2 programs are meant for those who have purchased or are about to purchase Miller pulsing equipment. In the first, we'll discuss the hookup of Miller pulsing equipment, and in the second, we'll take a look at the controls of the 60M series programmable wire feeders. Okay, we're finished with housekeeping. Now, what is pulsed MIG welding? Well, before I can give you a really good definition, we should talk about 3 other related types of metal transfer. The first is short circuiting, sometimes called short arc, or by its initials, SCMT, or by the official title of GMAW, or gas metal arc welding. This animation shows graphically how the wire leaves the contact tube in the gun, contacts the workpiece, and short circuits the wire electrode to the base material, causing the wire to heat and melt. Heat is also transferred to the workpiece, which melts at the point of contact, creating a pool of molten material. The molten wire is added to the pool, and the bead and joint are formed as the pool cools. These short circuits occur at a rate of 20 to 250 per second, depending on wire feed speed. With short circuit transfer, wire feed speeds, voltages, and deposition rates are usually lower than other transfer methods. Small diameter electrode wire is used, and the weld pool cools between each short circuit, allowing the process to be used for out-of-position welding. Production of some spatter and a potential lack of fusion on thicker materials are 2 limiting factors with short circuit transfer. During the globular transfer of metal while MIG welding, large globs of weld metal carried by gravity transfer from the wire across the arc to the weld pool. These globs, or droplets, are usually much larger than the wire diameter. Globular is a more unstable transfer with a rough weld bead appearance. The welding parameters, amperage, voltage, and wire feed speed, are higher than for short circuiting. Globular transfer occurs at amperage levels between short circuiting and spray transfer. Cold lapping or incomplete fusion may result from large droplets that splash metal from the weld pool, and there's generally a good deal of spatter. All things considered, there aren't many good things to say about globular transfer, but it can be used when bead appearance is not a critical factor. A spray arc transfer sprays a stream of tiny molten droplets across the arc to the base material. The droplets are usually much smaller than the diameter of the electrode wire. Once the spray arc has been established, it is said to be on all the time. Spray transfer is achieved using relatively high voltage, wire feed speed, and amperage. When parameters are correct, the spray arc produces a humming or buzzing sound. High metal deposition rates are achieved as a result of the high current density. A high degree of heat in the spray arc results in a large fluid weld pool, limiting its use to the flat and horizontal positions, and then only on materials of an 1/8 inch or thicker. Spray arc offers high deposition rates, use of larger diameter wires, good bead appearance, great fusion and penetration, and very little spatter. We've spent this time reviewing these 3 methods of metal transfer with the confidence that the review will help you better understand the 4th method, pulsed spray transfer. Pulsed spray includes desirable characteristics of the other three. You'll perhaps hear a number of different names for this transfer method. They may include pulsed MIG, pulsed GMAW, or GMAWP, the official AWS term. But keep in mind, they all mean the same thing. Metal is transferred by the same method as spray transfer, except with pulsed spray transfer, the welding power source, through its electrical circuitry, rapidly changes the current output between a settable peak or high current level and a settable background or low current level. The current level never falls to zero, as it may during the short-circuiting or globular transfers. Instead, the background current remains at a level that will sustain an arc, but will not transfer metal. By doing this, we get the high deposition of the spray process and the cooling of the weld pool and out-of-position capabilities like those found in short-circuiting. Pulsed spray combines many of the advantages of short-circuiting and spray transfer. Among them, the ability to use spray transfer on thinner material. An experienced welder will have success welding out of position and on materials as thin as 18 gauge, and there is little or no spatter. In fact, some users have chosen pulsed spray because of the appearance of the weld bead alone. It lends itself to high visibility welds, or those welds that are going to be chrome plated. There are many economies realized when using pulsed spray. Both thick and thin materials may be joined using the same lighter gauge wire. Thicker wire is less expensive per pound and is easier to feed through guns and drive rolls. This same advantage means guns, liners, contact tips, and wire feed drive rolls do not have to be changed each time workpiece thickness changes. There are many more advantages to pulsed spray welding, but they are related to the type of equipment chosen to produce the weld. We'll cover them in more detail during the next programs. And there are some disadvantages. The equipment required to do pulsed spray may be more expensive than equipment for standard gas metal arc transfer methods, and the shielding gas must contain at least 90% argon. Unless adaptable and/or pre-programmed equipment is used, setup for welding may be more difficult. We'll explain in detail during the next two programs. Using the pulsing process during certain applications and on some joints may result in limited penetration, especially on material over 3/8 inch. But again, adaptive equipment may provide satisfactory results. All in all, pulsed spray is an extremely versatile transfer method. It may be used on all weldable material. It may be used in all welding positions on nearly all materials. Few processes can accomplish this. It may be used on both thick and thin materials. And the versatility of pulsed spray allows economies in consumables. You'll recognize even more versatility during our next program, Pulsed MIG Welding Variables, where I discuss in more detail the pulsed spray waveform and how it may be modified to suit your application and materials.